In this lesson, we're just going to talk about how the logarithmic function is an inverse of the exponential function graphically. If you recall from Professor Messenger's video that logarithms are the inverse of the exponential function, the way that he showed it was saying if we're given an exponential function, for example, f of x equals 10 to the x, which we can rewrite as y equals 10 to the x, then the inverse of this is, well, how we find it. We would first need to switch x and y, so we would have x equals 10 to the y, and then we would solve for y. But the problem here is that how do we solve for y? We can't. What we need to do is introduce some new notation. So what we have is that we have x equals 10 to the y, which we can rewrite using a logarithm. So x equals 10 to the y would be the same thing as saying y equals log base 10 of x. Or, as Professor Messenger also mentioned in the video, in this case, when we have log base 10, that's actually what's called the common log. So we can say that this is equal to y equals log of x. Log without a base is the common log, which implies that it has log base 10. So what this is, in both situations here, this logarithmic function is just notation that we use for the inverse of the exponential function f of x equals 10 to the x. And we can see that they both have the base of 10, so we have 10 to the x for your exponential function, we have a log base 10 of x for your logarithmic function. So it's important to understand that that log is very much so related to the exponential function. They are inverses of each other. And for our purposes, log is really just notation to show that inverse of the exponential function. So now we want to look at the graphs of exponential functions and logarithms and how the graph of the exponential function can help us to graph the logarithmic function. So here we have that g of x is equal to 2 to the x and f of x is equal to log base 2 of x. So say the direction said to graph f of x equals log base 2 of x. Well, for right now, we don't really have too much information on how to graph it. So what we can do is we can graph our exponential function 2 to the x. If I was doing this by hand, I'd probably pick some values, make a table of values. You can even use your calculator, which is fine. So let's just pick some basic values for x, maybe -2, -1, 0, 1, and 2. And if I were to evaluate them, again, you can use your calculator or work through it by hand. We would plug in -2 for x, so we would have 2 to the -2. So 2 to the -2 would be rewritten as 1 over 2 squared, and 1 over 2 squared would be 1/4. Next, I would evaluate at x equals -1, so you would have 2 to the -1. Well, again, that negative exponent means we would rewrite it as 1 over 2 to the first. 1 over 2 to the first would just be 1/2. At x equals 0, we would have 2 to the 0, which would just be 1. At x equals 1, we would have 2 to the first, which would just be 2. And then at x equals 2, we would have 2 to the second, which would just be 4. So looking, although the graph is already here as a reference, looking at each of these points, we can make sure that they are all on the graph. So -2, positive 1/4, -1, up 1/2, 0, 1, 1, 2, and 2, 4. They all match up with the given graph. So now, as we saw in Professor Messenger's video, and also as I re-explained on the first slide, is that in order to graph our logarithmic function, since it is just an inverse of our exponential function, if we were actually solving it algebraically, finding the inverse of 2 to the x, we switched x and y and then tried to solve for y. Well, here, remember, with graphing our inverses, we would still switch x and y. So I made this table of values, and essentially what that means is that since log base 2 of x is an inverse, is the inverse of 2 to the x, that means that our table of values is just going to be switched around. So, whereas for g of x equals 2 to the x, I had the first order pair as -2, 1/4, for log base 2 of x, our first order pair would be flipped around. So we would have 1/4 and then -2. So no real work. We did all of the work before when we were finding the 2 to the x. Same thing, -1, 1/2. Well, the inverse of that for your log base 2 of x would just be 1/2 and then -1. 0, 1 would become 1, 0. 1, 2 would become 2, 1, and then 2, 4 would become 4, 2. At this point now, we have order pairs, we can get our graph. Again, we would want to approximate with those fractions, but we can get the general shape of our graph. So I would be plotting then 1/4 -2. Then I'd be plotting 1/2 -1. Then I'd be plotting 1, 0. Then I would be plotting 2, 1. Then I'd be plotting 4, 2. So we can see the general shape of the graph goes something like this. Again, with our inverses, remember the graphs are reflected over the line y equals x. So although they're on two different axes, if I draw that line y equals x, we can see, hopefully, that when reflected over, in either case, the 2 to the x or the log base 2 of x, the shape is very similar. Your log base 2 of x sort of levels off eventually as we're increasing, and it rides along the y-axis, whereas your 2 to the x would shoot up. So here is a way that we can graph our logarithmic function based on our exponential function, since they are inverses of each other. So now that we've graphed the function f of x equals log base 2 of x, it is important to understand more about the characteristics of the logarithmic function, especially as it relates to the characteristics of the exponential function. So I kept the 2 to the x and the log base 2 of x, but all of these will be true for your b to the x and log base b of x, which are inverses of each other. So recall that your domain of your 2 to the x function was -infinity to +infinity. And your range was from 0 to infinity. Well, if you look back at our graph for our log base 2 of x, we had a domain of 0 to infinity and a range of -infinity to infinity. So if we look at what happened, remember log base 2 of x is your inverse of 2 to the x. With inverses, you switch your x and y. That means that your domain and your range will switch, since your x's and your y's have switched. So the domain of 2 to the x is -infinity to infinity, which means that the range of log base 2 of x is -infinity to infinity. The range of 2 to the x is from 0 to infinity, so that means the domain of your log base 2 of x is from 0 to infinity. Again, switching that x and y means that your domain and your range have switched. Going back to your exponential function, we said that y equals 0 was a horizontal asymptote. Well, switching your x and y, that means that for log base 2 of x, we would have a vertical asymptote at x equal to 0. So x equals 0 being that y-axis. Again, your x and your y switched, so your asymptotes are going to have to switch. Another property that we had with our exponential function was if we were evaluating g of 0, this would be having 2 to the 0, and 2 to the 0 was 1, which means that the point 0, 1 is always on the graph of our exponential function 2 to the x, and really for all of our b to the x. Well, if we come over to our log function, if I evaluate f of 1, this means I would be doing log base 2 of 1, which would equal to 0, because remember, 2 to the 0 equals 1. In this case, for your logarithmic function, then, that means that the point 1, 0 would always be on the graph of log base b of x, or in this case, log base 2 of x. So for your exponential function, the graph always goes through 0, 1. Switching your x and y, the graph of your logarithmic function always goes through the point 1, 0. So it is important to realize that exponential functions and logarithms are inverses of each other, so their properties are showing that they're inverses of each other, and that, remember, this works for all b to the x and log base b of x because they are inverses of each other.